Welcome to our webinar for Fundamentals of Active and Passive Fire Protection System, Engineering and Design. If you can hear me properly, please type yes in our chat box, please. Perfect. All right, so we can begin with our introduction. Let me introduce you, Mr. 𝐏𝐬𝐬𝐢𝐯𝐻, our director, who will be starting our webinar.
Assalamu alaikum. Good afternoon, good morning, or good day, because we are conducting this webinar simultaneously in various parts of the globe, and there are different time zones. Today's discussion is an interesting one, and it's more closer to my heart. It's like regarding process safety, fire safety, HSE, and we like to clarify in the beginning. This is on the fundamental level, so it will be touching the basics, and with due apology from the senior people. So we are trying to cover from very fundamental things, and most of you might be aware, and then it will be going to the higher stage where the detailed engineering and field engineering concepts would be demonstrated as a case study. So fire is a chemical reaction involving rapid oxidation, combustion of a fuel. Three basically angles of a triangle, three sides. For example, oxygen, fuel, and ignition source. Like three things are normally required to have a fire. For example, when we talk about in a hydrocarbon industry, so it is always understanding that there is a hydrocarbons or petrol or diesel or other hydrocarbons inside the vessels and tanks and pipes, and there is a air outside which carries 21% oxygen, and if only one thing is missing, that is the ignition source. So that more focus is on the control of the ignition sources, so as fire should not be able to ignite. So that is the basic and fundamental concept of fire. Now, there are various kind of basically fire categories. As per Nfpa, we call them fire classes, like class A, class B, class D, and class K. Like for ordinary combustible materials, there's a class A, which fires are started from wood, paper, cloth, and then flammable liquid like grease, oil, paint, solvents, or hydrocarbons also. And this is class B. And then there are live electrical equipment or electrical panels, motors, wiring related fires, which are called class C. And then third one is combustible metals like magnesium, sodium, aluminum, and commercial cooking equipment like cooking oil, animal fats, and vegetable oils, which are category or class K. Why this classification is defined or designed? The main objective is the extinguishing material or extinguishing equipment are made according to these classes. Now, types of fires which are coming mainly from hydrocarbons and in the industry. We will normally cover listen two fires more. One is jet fire, another one is pool fire. Jet fire is normally in the high pressurized equipment, mostly with the gas, and it could be also led by the liquid sometimes if pressure is high. Like if there is a small hole or small leakage, and if fire starts there, so then that fire can, by the pressure of the liquid inside the container, may lead to few meters, maybe 50 meters, 60 meters, 100 meters, depending on the level of the pressure in the container or the piping system or fluid system. So that is called jet fire. And pool fires are like if a liquid from the tank is leaked to bonds or dike, then if the fire is there, so this fire would be like a fire in a basically a pond or in a you can say swimming pool. So that kind of fire is called pool fire. Then there are unconfined vapor cloud fires or flash fires can also take place. Running liquid fire, like if a open channel, then this could be running liquid fire. Then boiling liquid expansion vapor, which is BLAVI or firewalls. These fires are normally in tanks, and then there is also boil over. For example, if a tank is under fire, sometimes there is a liquid or water inside the hydrocarbon below, and when water boils, boiling point of water is earlier than oil, and that boiling water push the liquid or the oil in the tank for spreading, and that is called like a boil over scenario. And if the whole liquid is moving through, that's called Blavy. Then firefighting agents, like first we touch the various classes of the fire, and then now according to those classes, there are the fire fighting agents or the fluids which we use to fight the fire if the fire has taken place. For example, for cooling, smoothing, or dilution exposure, water is normally used, available normally. Then limitation is there, not for class C electrical fires. Freezes at 32 degrees Fahrenheit. Reactive with some material, for example, sodium and magnesium, cannot extinguish low flash basically point materials. That is for water. Then foam. Foam normally is a smoothing, or it isolate the excess of air or oxygen to the fire. Best for class B pool fires, two-dimensional fires, not for electrical fires. Again, foam blanket may break up, not applicable for LPG also. Then CO2 is normally for electrical fires, something reducing or eliminating the oxygen from the zone. Then non-reactive, non-residue, and good for class C, and reduces O2 level, toxic to people, like if like a CO2 system, or there could be a clean agent, what you normally use for the basically power substations and control rooms. Some CO2 is good for substations, and clean agents normally they are used in the control rooms. Then dry chemicals are also there, which are chain breaker, or you have to just like a sand, fire reflashes if not completely extinguished, or hot surface are present, especially flammable combustible liquids. Dry chemical can also be used to extinguish the fire. So there are, like you can see, 5 major type of agents which are used for firefighting. Like now there's a table, like which kind of fire agent is applicable for which kind of fire. Like if you see, these are the okay, right. So these are the various classes of the fire what we understood earlier: A, B, C, D, and K. And these are the agents: water, foam, dry chemical, carbon dioxide, wet chemicals, clean agents, and dry powder. So if you see, for electrical, the two only sources which are more effective: dry chemical and carbon dioxide, and clean agent, 3. 1, 2, 3. Whereas in normal, like a cooking oil, and there is only wet chemicals which are as a part of fire extinguisher could be used. Flammable metals, only dry powder is effective. Now, if you see flammable liquid and gases, which is normal hydrocarbon industry, so water is used for cooling only cooling, but is say not effective. Water is good for cooling. Then foam, dry chemical, carbon dioxide, and clean agents can be used there. For ordinary combustible material, water is good, then foam, then dry chemical, wet chemicals, and clean agents. So this is the combination. If we keep in mind, then it is easy to arrange various clean, like firefighting agents, to fight the possible fires which we may face in our daily life. Now, fundamental of the fire protection, like in a classification point of view, in terms of Nfpa requirements or Nfpa guidelines, like how we normally talk about fire protection, fire prevention. See, there is a small video. So there was one incident back in 1984, and this took place in Mexican City, which 1984, and it in LPG complex, it caused big, like a loss of life. 650 people died, 6,400 people there were injury, and terminal was also destructed. And the lesson which was learned from this incident was the layout and spacing allowed for escalation. The fire protection was basically minimal, system was not installed. Understanding of the potential fire hazard were lacking. Emergency isolation was not provided. These were the 4 reasons for this particular disaster which took place in Mexico, not very far away in 1984. So, various kind of standards are available for fire protection, but the more common and more commonly used in the industry are Nfpa, which is National Fire Protection Association of America, and it got various kind of basically standards which are used for various activities of the fire protection system. For example, Nfpa 10 is for portable fire extinguishers, daily use. Then 11 is for low, medium, and high expansion foam system. Then Nfpa 13 and 15 for basically water sprinkler system or water-based layout and PIMIC systems. Then Nfpa 30 is a more common one, flammable and combustible liquid and codes, which is used in the hydrocarbon industry. Then there is Nfpa 12 for carbon dioxide, and Nfpa basically 2001 is for clean agents for firefighting systems. So these are standards available. If we have access to these standards are very user friendly and we can easily follow their guidelines. Then American Petroleum Institute API has also issued certain guidelines or recommended practices to make easy understanding of Nfpa standards. Both API and Nfpa works hands in hand with each other. Like 2218 API RP recommended practice 2218 fireproofing practices in the petroleum and petrochemical processes. Fireproofing comes under fire basically passive fire protection. It is not part of active fire protection. We will be discussing next what is the passive and active fire protection. Then there is API RP 2001 fire protection in refineries. Then there is RP 2030 fixed water supply system fire protection in petroleum and petrochemical industries. Then API RP 2021 for management of storage tank fires. So these standards in API, they are made as a normal recommendations or guidelines so as we can easily understand Nfpa concepts and apply them in a more easy way as an engineer. Now, these standards, both Nfpa and API, are coming from American, basically industrial or engineering groups. And there are also standards which are coming from European Union side, like IP, Institute of Petroleum from UK or from European Union. These standards are also there. There's a big series of IP standards, and like a more common one is IP 15, which is used for hazard area classification, which is equivalent to older API 500 or nowadays 504. Similarly, IP 19 is for precautions of petroleum refinery and bulk storage tank installations. So there is a guideline available in the form of IP standards as well. So these standards can be compared in various scenarios. So Russian and Chinese standards, we are not still focusing, and in the coming years, maybe these two powers will also come back or maybe bringing their own standards as well. So fire protection versus fire prevention. Basically, I would say prevention and protection both works hands in hand, and protection means the science of reducing loss of life and property from fire by control and extinguishment. The fire protection includes fire prevention as well, detection of a fire and providing system to control or mitigate the fire and providing manual firefighting capabilities. It means this is not a versus, prevention is part of fire protection system. Normally, technology point of view, when we talk about hazards and risk management, five terminologies normally I remember as a normal layman. For example, first is prevention, second one is detection, third one is control, fourth one is mitigation, and fifth one is emergency response plan. So prevention means we have to isolate the hydrocarbons inside the containers. And number two, we have to control the ignition sources. And number two is detection. If somewhere hydrocarbon get leaks, it should be detected and we should be able to isolate. And third one is like ESD mean if prevention, detection, then is a control mean emergency shutdown system. If like before fire, we try to control or isolate or shut down the facility. And fourth one, in case if there's a fire, we should have a firefighting system. And under firefighting system, there are two: one active fire protection, other one is passive fire protection. Passive fire protection means if there's a fire, then building or the structure should not collapse quickly, and likely they are basically fireproofing is done for 1 hour fire rating or 2 hour fire rating, depending upon the applicable laws and practices. These are underwriter laboratories provide certain guidelines for that particular purpose. And then under the same prevention side, we have a firefighting system where all kind of firefighting system, whether they are like a water system, foam system, chemical systems, you are applying those various firefighting systems. Now, fire prevention activities whose purpose is to prevent fires from starting, and fire protection and fire prevention go hands in hand, as explained earlier. All fire protection programs include a fire prevention program. For example, control of ignition source is very important in minimizing the risk of fire, but does not meet the definition of fire protection in this guideline. Now, strategy point of view, what I explained earlier also, there are the 5 layers of protection: prevention, detection, control, mitigation, and emergency response plan. So the same concept, like a protection of personnel, is considered in the design of the protection system. Credible hazards have been identified, assessed, and understood and documented. Every opportunity to minimize the hazard has been identified, considered, and where practical implemented. Capital investment and estimated operating expenses to optimize with a view to minimize the hazard. Corporate goals can be met for the facility's lifetime. Potential adverse effect on neighbors, community, and the environmental are controlled. So, in a normal sense, what we do is a philosophy, like we want to have a zero leakage, or we wish to have no fire at all, or then HSEMS, which is called hazard. HSE is health, safety, and environmental related, or RMS means risk management system, or AIMS means AIMS, asset management system. So there is a, under HSE philosophy, there could be a fire protection, first of all, philosophy, then there are strategies, for example, like inherent safe design. Under part of strategy, we'll have an inherent safe design, then process safety management system, then project design reviews at a construction stage, safety management system, risk assessment, emergency response, fire protections. And the fire protection system, like whatever applicable system, those are basically installed, designed and installed. And then there is a procedure to manage and keep these systems ready, required drills or the functional testing of all the firefighting systems are also done as a part of this practice. Now, installed system versus emergency response, like in case of any fire, it is happening in the buildings, it's happening in the industry, and we hear the news about the fires almost every day. So there are three kind of system, I would say. Like one is when we say installed system, in addition to the inherent safe design, in addition to like you have operating manuals and you have a trained staff to operate the facilities, there is also firefighting system. And firefighting system also carry two parts. One is passive fire protection, as active fire protection. Passive means like fireproofing and those kind of things which prevent the collapse of the structure on immediate basis. Whereas firefighting system mean the water-based system, foam-based system, clean agent-based system, or portable extinguishers as well. Then installed isolation system, or basically it is the ESD system, like in case of any emergency, which can isolate incoming fluids and release the fluid by relief system or through flare system. Then emergency response, for example, if these things are trying to control the situation, but there is also emergency response. For example, if there's a fire in any bigger refinery or hydrocarbon plant, then it requires for a big fire a common or the joint response from the management and the company. Like who will be coordinating with the civil defense? Who would be coordinating with the district management or the security forces if you need help? Then who will be informing people and getting them to the emergency assembly points? And who will be counting them? Who will be coordinating all the actions? So emergency response plans are generally prepared by the companies, and those are also practiced as a drill. So as in case of any emergency, they can use it. So these plans are prepared for both buildings where a lot of people are living, or also applied for the offices in case of emergency evacuation. This could also be like not only relevant to firefighting. There could be an earthquake, there could be another kind of emergency, or there could be a sabotage as well, or third-party damage, bombing. In that scenario also, how the people would be reacting. So those emergency plans are prepared, practiced, and their application is checked if the emergency response would be able to react in case of any emergency. Then incipient firefighting, and if the fire become too large, protect exposure and walk away. Like there's another kind of things like how the people would be escaping in case of fire or big fire. So this is one thing which I discussed earlier also. There is also like a learning point of view, active versus passive fire protection. Active fire protection system requires some actions to occur before it function as its design intent. The action may be taken by either a person or a control system. For example, like a fire, water pumps, detection and alarms, gas sensors and detectors, sprinklers, water spray systems, water mist systems, foam systems, foam water deluge and water spray systems, clean agents, carbon dioxide system, dry chemical, steam snuffing, portable fire suppression system, hydrants and monitors, emergency isolation valve, ESD system. So I'm going through the same thing, maybe some feeling of repetition you might be feeling, but as I said, we are going stage by stage from the basic definition to the next case study side. So it's to make you familiar what is active fire protection system. Now, when it's a passive fire protection point of view, so these are the actions which you try to minimize the effect of the fire. Like if fire is there, you can minimize or which may eliminate the chances of the fire as well. For example, fireproofing, which I explained earlier, is done by mastic material or cement. Then spill containment or drainage, which is diking is also part of that. And then to minimize the fire effects, the firewalls normally made at offshores. Then to prevent hazard area like ignition sources, hazard area classification process is done. All electrical equipments and instrumentation equipments are installed in a way they are explosion proof as per like IP requirement or ATEX requirement. Then prevention of static electricity, lightning protection and state current protections. Then physical separation of units and buildings and safe distances from various installations. So then like there are automated firefighting systems and manual firefighting systems, both are available, and we can see that like it's very, I think, automated activation is you can activate is based on the any by the detection system. If, for example, if you got a fire and gas detection system based on the fire zones and the number of detectors in each fire zone, confirmation of the event, automated like a spray of water or foam can be started, or the system might be activated based on the automated signals, or it could be manual startup. or manual activation, or it could be a semi-automated systems as well. So the automated systems are normally costly, and it may also may sometimes have a false signals, and that may create a panic. However, automated systems are if maintained properly are more preferable as compared to the manual systems. Now, isolation means what? Isolation means if there is an event in a plant and there is hydrocarbon coming to the plant from other facility. So due to ESD system or due to manual system or due to ESD valves, the incoming fluid should be stopped. And it is called isolation or stopping the incoming fluids. And these are the various kind of valves are there which are used for manual isolation or emergency isolations as well. So other thing is the relief system, that will I think coming next, but the relief valves are also there which are used to basically evacuate the fluid or remove the fluid from the containment, and the PSVs are there, pressure safety valves are there, normal blowdown valves are there, and these are leading the fluid to the atmosphere or to the flare system as it is designed. Then like in normal it is, as I read the content of the presentation, if you see a P and ID, that makes more easy, and various kind of isolation valves, isolation philosophy, positive isolation, like two isolation valves with bleed, drain, or one isolation with spectacle blind. So these aspects are there, and then boundary limits are followed, between plants and within the plants. Various kind of valves are used as a part of process plant design as a P&ID part. Depressurization is the other part which I mentioned. The one is isolation, where you try to basically isolate incoming fluid by ESD valve, which is automated one, or it could be by manual or motorized valves also. Similarly, if you want to relieve the containment of the plant in case of any emergency, so there could be a relief to atmosphere, if it is a gas, or it could be through flare or burn pits. And the relief valve point of view, there are PSVs and there are VDV valves, both are there, or vents are there. So depressurization is also required in case of any emergency. It's also called emergency relief. API 520 and API 521 provide all these guidelines basically for the use of relief systems and designing of the relief systems as required. So there are various causes are there to initiate depressurization, but it is a part of emergency response or mitigation system. It says what the pressure benefit of the depressurization as a part of the proper definition in text point of view. There is a significant reduction in the chance of rupture if any pressure vessel exposed to fire due to depressurization. The driving force behind pressure jet flame is rapidly decreased. The leakage rate of the liquid spilled will be decreasing as well. The same is the purpose for the isolation as well. There are several advantages of vapor depressurization, including the following: an automated refrigeration effect may be produced in the pressure vessel, which provide cooling of the liquid as well due to Joule-Thomson effect. The need for a liquid blowdown system is eliminated by retaining liquid in the vessel as a heat sink. Any increase in temperature of the wetted shall be minimized. Emergency response, as I said earlier, I explained a little bit. All major companies are making documented emergency response plan. They make various scenarios. For example, if there's a small fire, if there's a big fire, or if there is a blavy, or if there is a boil over of the tank. In those scenarios, in addition to the existing firefighting system, if the industry or the plant would be calling for the civil defense force or other security forces or other external help, that would also be provided. How the actions would be coordinated within the organization, and if there would be some control room for emergency, who will be talking to the media to inform, because if there would be a fire, there would be news and people would be watching it. So media would be watching, they would be waiting for the people, the information from the company. So, starting from media interface, the role and responsibilities of the people, of the leadership in case of that emergency, if there are some fatalities, how to manage them, if there are some injuries, how to take the help of the nearby hospitals and so on. So, all the scenarios are basically built, and accordingly the response is planned and documented, and that is practiced also as a dry run. So that is basically how oil and gas industry is working. Now, as a context point of view, as a text point of view, emergency response has a significant influence on a company's fire protection strategy. The question is to fight or not to fight fire at a facility. Emergency response is one of the last layer of protection, which is normally called runaway. No matter how a company may provide emergency response, they must comply with the federal, state, and local regulations. Emergency response can be internal resources, external resources, or combination of both. As I said, civil defense, hospitals, and district management in other countries, right? The degree of internal response can vary from a basic ability to properly respond with fire extinguishers and sound the alarm to a fully fledged industrial fire brigade with internal structural firefighting capability. External response may include local fire department and mutual aid organizations like hospitals. Then active fire protection system. Okay. So these are the what are the normal main active fire protection system name I have given. So we'll be giving a little bit more details now. So still 48 slide, we have to go through the 199. So we'll be having one break in between this question answers, then my colleague will take over. So like when we have firefighting system, so how we know how much water is required? So the first thing is what is the size of the fire would be, what could be the requirement of spray density of the water in that particular area, and then overall water requirement are required to be estimated. So if I go by the definition of the text, the fire water demand is the maximum rate of water that will be needed at any one time and applicable to the single fire. Thus, the requirement of the largest single fire contingency will determine the capacity and design of the fire water system or fire tank. And then the issue is also whether the capacity would be for 1 hour or 2. That would also be defined based on Nfpa requirement. Like in normal refinery fire design, we try to estimate water requirement for the tank farm, for the jetty, for the process plant, for utility areas. And normally tank farm is the leading basis for the determination of fire demand for the fire water system. Water demand for other areas within plant may include, utility plant loading racks, office buildings, cooling towers, other areas, but we have to see what is the worst fire requirement. It is not assumed that fire would be everywhere. The single fire scenario is assumed, and cooling is provided to the neighboring plants or neighboring area. Fire water demand, continuing the same subject. If the designed water flow rate for the process unit requiring the largest flow is less than the requirement for the largest tank or group of tanks, then tank protection demand should become the design basis of the water, as I said earlier. The capacity is based on number of factors, including source of water available, reliable of makeup water supply, then potential to escalation to other areas of the facility, isolation philosophy, and the ability of depressurization the process unit. The reliability of the fire water supply should be such that the loss of any one source does not result in a loss of more than 50% of the flow of the water. Water distribution, there's a fire mains are there, valves or fittings are there, fire hydrants and monitors are there, and fire water takeoff points are there, and same water may be linked with the foam system as well. So fire main means a fire water main piping system, which is bringing the water from the fire water tank through the pumps to the facility. Then valves and fittings for isolation, fire hydrants normally, as you can see here, to throw water to the fire destination. Fire water pumps is the main pump. Normally there are 3 pumps installed to manage fire water distribution system. one driven by diesel engine, other driven by motor, electrical motor, and third jockey pump to keep the system pressurized all the time. It is a low capacity pump, and normally both pumps are having the capacity of 100% capacity each. See, and there could be, if the more pumps are there, then there could be a lower capacity as well. Nfpa 20 is providing the guideline for the pump selection and design. Detection and alarm is a fire and gas detection system. Normally we call fire and gas detection system, or smoke detection system, heat detection system. Nowadays in buildings also there are various kind of detectors are there, and in plant areas you will have a gas like hydrocarbon gas detection, toxic gas detection, heat detection, and smoke detections. So those things, these detectors are installed by designing a proper fire and gas detection layout with a due voting system, and the selection of these detectors are done as per the process requirements, and the multiple combinations are installed. For example, if there is a gas detection, if there should also be some heat or the smoke detection, or toxic detectors as well in the same area, H2S is also there. So by combination of one or two detectors, the event occurrence can be confirmed by the validation of the two signals at a time. Now, a number of factors which must be considered in the design of reliable fire detection and alarm system are data on the nature and arrangement of power resources, coverage provided by the system, alarm function on loss of system operability, suitability of detection devices for the risk involved, other kind of process applicable, testing and maintenance procedure to ensure a reliable system, then consequences associated with the false alarms as well to be considered. Sprinkler system we see always in the car parks and normal buildings, and also they're parts of the hydrocarbon industry as well. The main purpose of sprinkler system is the cooling and the extinction of the normal fires, right? Sprinklers are the most common fire protection system and used today. The success of fixed water suppression system depends on the following: adequate and reliable water supply, adequate water density, automated actuation of the system, effective water spray patterns, alarm that indicate the operation or the malfunction of the system, effective maintenance and testing of the system as well. Now, in sprinkler system point of view, there are like a wet pipe, dry pipe, pre-action, deluge system. Like in normal case, like where the full system is filled with water, and in case of any emergency, water can straight away could be thrown to the destination to extinguish the fire or to cool the environment. A dry pipe means there are deluge valve, and the downstream part of that valve is mostly dry, and in case of fire, the system is activated. So there are pros and cons of both systems, and both systems are being used. Then principal, like a pre-action mean, the principal difference between pre-action system and a standard dry pipe system is that in pre-action system, the water supply valve is actuated independently of the opening of the sprinklers. Deluge protection can be applied over the entire hazard area with open sprinkler heads located at various floor levels, or fixed water spray system can be applied, especially on the equipment to be protected. The design of spray system should be in accordance with Nfpa 13 requirement. So water spray system and sprinkler system little difference. Only the sprinklers are more organized sprayers, and they are rotating and are by the nozzle. But if the water is sprayed through a nozzle, that's called water spray system. A water spray system is a hydraulically designed with open spray heads to protect a specified hazard. The term water spray refers to use of water discharged from a nozzle having a predetermined pattern, drop size, velocity, and density. While deluge system are for the overall protection of the given area, water spray system can be installed for the protection of a given area, specific equipment, and hazard. Water spray systems are used for protection against hazard involved gaseous and the liquid as well. The design of water spray system should be in accordance with Nfpa 15. Water mist system. There are some nozzles which are like flammable and combustible fluid they can use. Electrical hazard also, because they are having very less amount of water. This could be used for the electronic equipments as well. Foam system. Foam system normally, if you see that like for the storage tanks, especially for the floating roof tanks, so foam system is installed to focusing on the ring main fires. So there are pourers of the foam, and now foam got two things. One is the substrate or chemical, and then the water. And there's both foam and the substrate and water both are mixed at the time of activation, and then foam is thrown on the destination. So in normal, like concept point of view, it is not pre-mixed product, and the both system should be kept ready, or what is going to the foam or the substrate and then going to the destination, or they mix somewhere somehow in between by mixers, and then it's thrown to the destination. So there are various types of foam systems are there, and foam is primarily used for assuming two-dimensional surface fires involving liquid that are lighter than water. Foam may be used to insulate and protect against exposure to the radiant heat. Because of water content, foam may be used to extinguish surface fires for ordinary combustible materials. So the low expansion foam with expansion up to 20 times, medium expansion foam 20 to 200 times, and then high expansion foams are also there, which expands from 200 to 1000 times foam solution volumes. Foam system have more components requiring higher maintenance and have somewhat lower reliability than water spray system. And Nfpa 11 provide guideline for the foam system. Foam application point of view, there are fixed system, semi-fixed system, and portable systems are also there. Fixed system are like a completely installed on the tank foam, right? Pipes from a central foam station to the tanks or equipment discharging through fixed delivery outlets. Semi-fixed system employ fixed discharge outlet connected to a permanent piping that terminate at a safe distance from the tank or the equipment to be protected. Portable system contain no fixed foam piping. Foam is delivered to the spill or to the burning surface by hose stream or by portable monitors. Foam proportioning methods, like how the foam is made. Like in order that a predetermined volume of liquid foam concentrate may be taken from its source and placed into a water stream to form a foam solution of a fixed concentration. The following two general methods or classification are used. Method that utilize external pump or pressure to inject concentrate into the water stream at a fixed ratio, balanced pressure system, or the method that utilize the energy of water stream by Venturi action and orifices to induce concentrate or substrate. Typically, such device impose a 35% pressure drop on the water stream. So when what like I explained earlier, also both the chemical or substrate should meet or should be mixed with the water by some mechanism. These two basic options are available in the engineering. Application of foam or suppression on the tank foam. This was the one example I gave. It was a fuel, and it could be like a whole. If it is a fixed roof, then foam is thrown on the whole surface of the tank, right? And it is like a minimum number of foam chambers, subsurface class 1B, 1C at liquid point of view, then subsurface class 3 liquids. So how many, if this is the size of the tank, how many pourers are required? These are the number of pourers of the, like this foam chamber, the number of chambers which you need to install to cover the full tank. What a Deluge system, like if there is a, like you can see it. So this is a piping system, and this piping system leading water sprinkler system there, and there could be also hydrant nearby, and this water spray through nozzles, or also maybe providing fluid to the foam system as well, linked with Deluge system. The foam water sprinkler system is basically the same as sprinkler system, except foam concentration concentrate enough proportionate into the water, causing foam to be discharged. This system can flow either water or foam effectively. The foam system should be designed in accordance with Nfpa 16. The foam discharge rate for a foam sprinkler system should be at least 0.16 GPM per feet square. The foam discharge should be continuous for a minimum of 10 minutes. With the exception of high expansion foams, all other foams can be used in foam water sprinkler system. Clean agents. Clean agents are like FM200, normally called, I remember the one name, which is used for substations and for control rooms. Clean agents are electrically non-conductive, volatile, or gaseous fire agents that do not leave a residue. Clean agents fall within two categories, hydrocarbons and inert gases. Typical hydrocarbons include hydrofluorocarbons, or the hydrofluoro names are there, and typical inert gases include argon, nitrogen, carbon dioxide, or combination of these agents. Clean agents can be used to protect like enclosures containing electrical and electronic equipment, subfloors and other like concealed spaces, flammable and combustible liquids, telecommunication equipment. The design of clean agent and fire protection system is normally Nfpa 2001 requirements. Then carbon dioxide is also part of the clean agents as well, but it's like a local application of total flooding, and this system is also applied for the control rooms and electrical substations. Dry chemicals we are all familiar with, and if they are placed across, they can be used in emergency sites, and they are more effective when being used by the humans at the case of small fires. Dry chemicals are recognized for their unusual efficiency in extinguishing two-dimensional fire involving flammable liquid. Fast extinguishing action is achieved provided the agent is used by the user effectively. These agents are effective on smaller spill fires. If there is a risk of reignition from embers or from hot surfaces, these ignition sources should be quenched or cooled with the water and the subsequent. Dry chemical agents are non-toxic and are suitable for extinguishing clothing fires of individuals as well. Portable fire suppression equipments. There are various kinds of fire extinguishers we see all around, and these equipment include fire extinguishers, fire water monitors, foam eductors, foam tanks, water tanks, special high flow nozzles, and so on. So portable, they could be based on the size, or there are the fire trucks which are carrying these fluids. And when we say like a portable fire suppression system, there should be proper layout based on the physical layout of the site, the hazards of the process, and fixed fire protection system. Additional fire suppression equipment may be required to effectively manage a fire emergency. Portable suppression system equipment assist in providing the fire protection for the equipment involved in emergency. So there are various kind of like fire extinguishers. Use of this portable system, the cost of fixed system may not be acceptable, or the fire water supply may not be available or limited. So before we start the case study, and we will be taking certain questions now, and afterwards also like 135 slides are there. It is a long distance to go, and time wise also 1 hour or maybe 1 hour 30 minutes it will take. I hope people will bear with us, and now we will be answering some of the questions.
Okay. One question from Mr. Nazmi. How do we decide whether we need the firewalls or a blast wall for the facilities? How do we calculate the rating of the wall?
See, there are basically QRA studies are run, and where the fire zones and contours are designed by the QRA study, and then accordingly the effects are minimized by conducting the fire wall. For example, in offshore, there is a utility area and there is a neighboring hydrocarbon equipments are there. So if you want to install all equipment in a utility area, which should be, let's say, as a non-classified, because cost could be lesser. And secondly, we don't want the hydrocarbon should be affecting that area, or there could be a living quarters in that particular vicinity. So for that living quarters as well, we need to minimize the effect. So in this way, the QRA modeling and dispersion models provide the location or destination where the fluid may affect, and if those areas are required to be protected from the fuel leakage or the rupture effects or fire effects, then accordingly fire walls are installed and the ratings are defined based on like a UL requirement, whether 1 hour fire rating or 2 hour fire rating, on that to prevent the pressure as well.
Okay, next question. I want to ask about fire protection for LNG production or LNG terminal facility. Is there any special consideration in defining fire protection for LNG?
See, LNG is just like a gas, because LNG is normally liquefied natural gas. And uh, in terms of like normally, if let's say if LNG tank is leaked, so there could be a Joule-Thomson effect, and the balance LNG will convert into ice. So in general, LNG fires are not so dangerous as compared to LPG fires. LPG fires are more dangerous, and LNG fire, the normal hydrocarbon gas or methane kind of fire protection system is required. Like normal foam system, normal sprinkler system, no specialty as such.
Next question. How to optimize fire protection at instrumented safety system plants?
See, fire and gas detection system like is a part of like the fire and gas like firefighting system or fire prevention system, and the fire and gas detection system is designed in accordance with IEC 61508 and IEC 61511 requirement, and their reliability level and SIL level are maintained as per applicable SIL requirement. It is a part and parcel of the system. Similarly, ESD system or blowdown system, those are also part of the ESD system, and applicable SIL requirement are determined as per IEC 61511 requirement.
Okay. Next question. Can you please explain what is diking?
Dike are the bund walls, like when the tanks are built, 3, 4 tanks or 1 tank, if the tank leaks, you don't want to have a liquid of the tank reaching everywhere. So you need, build certain like bunds or walls, that's called diking. So as the fluid is remain within a controlled area rather than spreading everywhere in the facility.
Another question. Is there any suggestion on how to quantitatively review adequacy of fusible plug loop in terms of the quantity and coverage?
Can you read the question again?
Is there any suggestion on how to quantitatively review adequacy of fusible plug loop in terms of the quantity and coverage?
See, the type of detectors when you are attaching there, right? So you have to cover or you have to provide enough number of detectors, whether heat or it's a smoke or toxic gas or gas, so as you can have enough guideline or assurance from the detectors that there is a event. Basically, through these detectors, you wish to confirm the occurrence of the event, so as a protective action could be taken. And there are like relevant standards which gives you the coverage area, and vendor and manufacturer of these plugs or the detectors also provide like how much area could be covered by one plug, and then accordingly number of plugs are estimated.
Okay. Next question. For a hydrocarbon pump station, what type of fire extinguisher would you advise I position there, or he will position there?
See, in general, for the pumps areas, if they're like operating at high temperature, water sprinkler system or Deluge system is installed, right, and supported by manual fire extinguisher systems as well through powder, and so because the foam system is generally not so effective on the pumps.
Next question. Are pressure relief systems used for depressurization?
Normally, see, it's a standard part of the plant design. You have to provide relief system. Only PSVs are maybe open to atmosphere, or they might be leading to the flare system. And these relief systems are designed in accordance with API 521, and 520 is about the PSVs, but there are venting system, flare system, or burning pit system, and all kind of relief systems which are applicable on any given facility should be designed and installed.
Okay. One question. Please let me know whether 4-hour duration of fire water supply is as per NFPA.
See, generally, as I remember, 2 hours also there. 2 to 4 hours. The numbers are there, but I don't remember exact. Like 4 hours is not. I'm sure 4 hours is too long to have a water quantity. Facilities may not be able to maintain.
Okay. Another question. In the start, we used to say water is not good for electrical fire. Now we are saying water mist system is good for electrical fire protection. What is the reason?
See, the compromise. See, a water mist system is one option available, but it is not an ideal one. And like as a process engineer, I do not believe like when you're throwing a mist on any fire on electrical, it will not be throwing the water. But if you can ensure that the mist nozzles are so adequate that only mist will go, or like a fog will go rather than water will go, then it is effective, or at least it can help to eliminate oxygen from that area.
Okay. Next question. Using foam extinguisher on LPG, is it correct or wrong?
See, on LPG, depends on if you're doing LPG spheres, right? Mostly it's cooling, and foam should be thrown on a surface which can isolate the area. And normally spheres, foams is not effective, right? Only cooling is effective, and other parts like normal, they mostly depend on the relief system in LPG, because LPG, if repressurized, it will release to flare. And firefighting concept point of view, on the piping system is a combination of Deluge system, spray system, and some foam can also help.
Okay. Next question. How to classify the size of the fire and how to compute the number of fire extinguishers available to mitigate the fire, considering there is an automated CO2 system also.
See, CO2 system is for the closed area, substations, and control rooms. However, the other fires where you're providing fire hydrants or hoses or the sprinkler system, that depends like a process area, total surface area, the kind of fire which may occur, what kind of fire density you need to spray, and what's the coverage area of each hydrant, and then accordingly the number of hydrants and their water demand requirements are established.
Last question before proceeding. Shall sprinkling system is tested, and how often shall we test the sprinkling system in a manufacturing site?
See, sprinkler system is normally when installed on the facilities, each company defines their own interval. It may vary from 1 to 2 years if you are having the functional testing facility available, and there's normal frequency of the testing of the sprinkler system, 1 to 2 years, once.
One more.
Thank you very much, and my colleague Mr. Frost will continue the balance part of the presentation, and then we'll have a question answer at the end again.
Thank you, Mr. Ejaz. Okay, let's proceed. Now we will discuss the basic engineering study for the fire risk assessment implementation. Basically, it was a case study. So first of all, we will go through the objective of this project, which we have performed this case study, and the scope which was provided. So basically, the project background was there was an HSE gap assessment audit was done for all the upstream facilities of the client, and there were various recommendations that were made to improve the following systems. Number one, fire and gas detection system, active firefighting system, passive firefighting system, HSEMS and associated control procedures. So we have to carry out the feed engineering and development of HSEMS related documentations in accordance with the requirements identified during the gap assessment studies. Project objective was to perform the field engineering for fire and gas detection system. We have to design the active and passive fire protection systems and the development of HSEMS related documentations in accordance with the requirements identified during the gap assessment studies. There were different facilities, so we have received different scope of works for their different facilities. For the facility A, we have to calculate the firewater demand, and then we have to design the automatic gaseous flooding system for the control room and the electrical room, and then we have to design the automatic sprinkle system for the living quarters, that how many sprinklers are required for the living quarters, firewater curtain system at escape routes, and then we have to remove the existing detectors and we have to install the new toxic gas detectors and flammable gas detectors. Then we have to calculate that how many number of detectors will be required in that specific area, and new instrumented automatic fire detection for process equipment for all the production platforms. Similarly, for the facility B, the scope was to remove the existing detectors and install the new toxic gas detectors and flammable gas detectors, and then to remove the existing detection and design and install new fire detection system for building and process equipment with centralized control system. For the facility C, bladder tank foam system in place of PPT system with 100% connected reserves, number of foam chambers to be designed as per Nfpa 11 standard, automatic gaseous flooding system for MCR, sprinkle system for dining hall at camp A, C, and lab, etc. Then to remove the existing detectors and to install the new toxic gas detectors and flammable gas detectors, and to remove the existing detection and design and then install new fire detection system for building and process equipment and tank farm with centralized control system. For the facility D, the scope of work was the additional requirements for FM 200 system at station control room, then to remove the existing detectors and install new toxic gas detectors and flammable gas detectors, and to remove the existing detection and design and install new fire detection system for building and process equipment with centralized control system. So these were the scope of work, and these are the execution methodology. We have executed this project by following these steps. Project starts with the kickoff meeting, and then the collection of the data, and then the site surveys, site visits, collection of required information, and then the updating of the design basis memorandum. Then FNG mapping study we have performed. Then we have checked the existing firewater system adequacy and integrity as per the scope. And then we have prepared the engineering deliverables. We will discuss what were the deliverables, and then review and internal QA/QC checks, and then cost estimation, purchase, requisition of long lead items, and EPC tender package as well. So this was our methodology: site surveys, collection of data, and then followed by the submission of site survey reports to the client for his review and comments, and then detailed study and checking of adequacy of integrity of existing firewater system, and then preparation and updation of design basis memorandum, and then performing the basic engineering study, FNG mapping study for the selected area under the scope. And then issuance of engineering deliverables, review and comment cycle, and then submission of the basic engineering dossier, and then preparation of EPC tender package, including the scope of work for EPC contractor, cost estimation for EPC work, project execution schedule for EPC work, RFQ for long lead items, as well as then submission of EPC tender document, and followed by the submission of all final deliverables. This was our project execution methodology. These were the standards which we followed: national or local standards, client standards, National Fire Protection Association, NFPA, HSE UK Executive, American Petroleum Institute, IP standards, ASME standards, Shell best engineering practices. These are the reference code, and these were the list. This is the list of major deliverables. We have submitted the Firewater demand calculation report, design basis memorandum, basic engineering design data, project coordination procedure, document numbering procedure, document control register, site survey and document retrieval report, project basic design dossier, EPC scope of work, cost estimation, EPC tender package, as well as project execution schedule, bill of materials or quantities, project HSE plan, long lead items list, long lead items RFQs, specification of material procurement, specification of test and commissioning, QC procedures, site test specification, and as well as transportation vessel requirements. These were the list of major deliverables. Now we will discuss that how we can design a sprinkler system. So in order to respect the confidentiality agreement with our client, we have changed some input data and the results for the demonstration purpose only. So sprinkler system design at the facility quarters. So basically, there were some gaps and recommendations which were identified in the RFA report. These were that at the living quarters, which was without the sprinkler systems, the personal life, the life of a personnel is at risk, as chance of escape will be less, especially in offshore platforms. For example, if it is offshore platform, then the chance of escape is less, and the potential loss of life will be high. The people life is at high risk as living quarters fall within the radius of 12.5 kilowatt per meter square radiation from production operator at CPF platform. Living quarters at CPF are to be protected with automatic sprinkler system. The automatic sprinkler system is to be designed as per the Nfpa 13. So this was the recommendation that it should be designed as per the Nfpa 13, automatic sprinkler system. So for the implementation of this recommendation, below are the listed 3 levels of living quarters at CPF, where we have to provide, where the automatic sprinkler system has to be provided. One was main deck level, second was level 1, and the third was level 2. So these were the 3 levels in which there should be a automatic sprinkler system. This is the design criteria. Nfpa 13 standard for installation, which this is Nfpa 13 is the standard for the installation of sprinkler system. It is mainly referred to for carrying out the design of sprinkler system for living quarters at the client's facility. Living quarters are considered ordinary hazard occupancies. It lies in the category of group 2. Wet pipe sprinkler system is considered for living quarters. Flangeable glass bulb type sprinkler nozzle having temperature rating range from 57 to 77 degrees centigrade is selected on the basis of maximum ceiling temperature, which was 38 degrees C as per Nfpa 13 table 6.2.5.1. The maximum allowable protection area of coverage of for a sprinkler is taken as 130 foot square, or we can say that 12.1 meter square as per Nfpa 13 table 8.6.2.2.1-B. So this is the standard area of coverage. The maximum spacing between the sprinklers is taken as 15 feet as per the Nfpa table number 13, Nfpa 13 table number 8.6.2.2.1-B. The spacing between the sprinkler branch lines is taken as 12 feet on the basis of maximum coverage area per sprinkler nozzle. The dimensions, length, width, and height of each room at all the 3 levels of living quarters are measured during the site survey and marked on the layout, living quarter plans, living quarter side elevations, Then the layout drawings are developed as per the dimensions measured during the site survey. The elevation of ceiling for all the rooms at living quarters is 2.27 meter or 7.45 feet, as pendant types sprinklers are considered. So these would be installed at ceiling level. The elevation of the main deck from trident 7 level is taken as 3 feet. The design density for sprinkler system for main deck level and the level 1 and 2 living quarters is taken on the basis of calculated area as per NFPA 13, figure 11.2.3.1.1. 10% additional water demand is considered in calculation for hydraulic imbalance as per standard engineering practice. Fire hydrants are already available at living quarters, so no hose stream is considered for the sprinkler system at living quarters. It is to be checked and verified during the EPC stage. Hydraulic calculations are performed by using pipelet software, module version 1.5. Hydraulic calculations are carried out on the basis of Hazen-Williams equation as per section 23.4.2.1.1 of NFPA 13. C factor used in Hazen-Williams equation is taken as 120 as per the NFPA number 13, this table. And then water viscosity and density are taken as 2.42 pound per foot hour, and this respectively at 68°F for hydraulic calculations. Nominal K factor for the pendant type nozzle is taken as 5.6 GPM per PSI, or half-inch NPT is considered as per NFPA 13 table this for Firewater sprinkler nozzle. The equivalent length of Firewater pipe is considered as 1.5 times the pipe's straight length, since piping isometric are not available at that stage. Minimum operating pressure at remote sprinkler nozzle is considered as 0.482 bar as per NFPA 13 section this. The minimum required pressure at all three sprinkler systems inlet tie-in points is hydraulically calculated on the basis of minimum required pressure at remote nozzle. Normal allowable velocity limit for Firewater sprinkler system is considered as 6 meter per second as per NFPA 20. Maximum friction loss value is considered as 1.5 bar. For the central processing facility living quarters area, the existing Firewater piping layout and the PNRDs were not available, so the Firewater tie-in point for the sprinkler system is not identified. However, Velosi understands that the tie-in connection for the sprinkler system can be taken from the discharge header of the Firewater pumps installed at living quarters or trident 3, and where discharge pressure is 8.13 bar as per the report, FRA report. Fresh water is considered for Firewater sprinkler system as Firewater at CPF trident 3 area is fresh water referred from RFA report as well. So now we are going to the calculation. There were two men's rooms. Two men in that room. The capacity for the person is 2. Length of that room is 15.28 feet. So we have the length, we have the width. We can calculate the area by multiplying the length and the width. And then, as per the NFPA 13, the coverage area we have known that it is 130 feet square. So now we can calculate the number of sprinklers required for each room. Area divided by the coverage area. Area of that room, it was 108.344, length into width, divided by the coverage area per sprinkler as per NFPA 13 was 130. So we are dividing this. So we are coming with at least 1, rounded up 1. So in that facility, there were total number of 2-man rooms were 10 and 4-man rooms were 2. So total number of rooms were 12, and total number of sprinklers required for all the rooms we can calculate by multiplying 1 by 12. So we are having the value of 1300 feet square. Total area of the room is this. Similarly, for the warehouse, the length of the warehouse was 15.28 feet. Width was this. We can calculate the area, and the coverage factor as per Nfpa 13 per sprinkle is 130. So we know by dividing this factor, the number of sprinklers required for the warehouse was again 1. Now the sick bay, the length was 15.28 feet, the width was 13.48 foot. The area, we are dividing length into width, and then coverage area per sprinkler as per the Nfpa 13 is 130 feet square. So the number of sprinklers required for sick bay is area divided by the coverage area 2. Similarly, for the laundry, we have performed the same calculations. For the main corridor as well, the same calculations. So here the length was greater than the previous cases. So now the demand of the number of sprinklers is higher than the previous cases. So overall main deck calculations are total number of sprinklers required are 23, total area which they have to cover is this one, and the density as per Nfpa 13 it should be this. Firewater demand we can calculate by multiplying the design density to the total number of area. So we can calculate the firewater demand. Firewater demand with 10% hydraulic balance is we can multiply this with 1.1. We will get the firewater demand with 10% hydraulic balance. So the hydraulic calculations for the main deck level living quarters are performed using the pipe net, which have different modules. So we have utilized the sprinkle module. The version of this pipe net software was 1.5. The analysis has been performed as follows. For sizing the sprinkler system network at main deck level living quarters, line sizing is performed by verifying maximum allowable velocity is not exceed at any point in the network system. For finding out the required pressure at each sprinkler nozzle and at inlet of sprinkler system, so that each sprinkler nozzle pressure is maintained at minimum of 0.48 bar gauge or 7 psi G pressure. So this is the input data. This is the reference input data for the hydraulic calculations of the main deck level sprinkler. This is all the input data. So the conclusion of this part of the scope is that for the installation of firewater sprinkler system at CPF living quarters, refer below for the hydraulically calculated firewater demand and time points pressure for all the 3 levels of living quarters. For example, for the main deck level sprinkler system, the firewater flow rate requirement was 495 gallons per minute. Similarly, for level 1, level 2 sprinkler system, we have calculated in the similar manner by utilizing the pipe the software, and then these are the results. Now let us discuss the gaseous flooding system design. So this is a demonstration of FM200 automatic activation. For example, this is a server room. Detectors, so there are two basically zones, zone 1 and zone 2. In zone 1, there is a fire, and the detector in zone 1 is activated. It sends the signal to the extinguishing control panel, and it sounds the alarm. Alarm bell is activated. Then the smoke reached to the second zone of the detector as well. pre-discharge alarm or on is activated. Then all the air conditioning and all the ventilation system is closed, shut down. So there are 60-second countdown. For example, if it is a false or spurious activation, somebody can go and press that button to abort the process. If not, then after 60 seconds, it will send the electrical signal to the solenoid and it will activate a valve releasing pressure. Then FM200 is discharged and extinguish the fire. So in this way, the automatic activation of FM200 is carried out. So now, similarly, like we have discussed in the previous case, the sprinkler system. So there was a recommendation in the FRA report as well that the basic engineering for the installation of automatic total flooding gaseous extinguishing system for main control room, including powerhouse control room and UPS room at main control building, offices and meeting rooms are not included in the scope of work. And these are the design criteria. As per the scope of work, the main control room, including powerhouse control room and UPS room in the main control room building, are considered for the design of total flooding gaseous suppression system. 50 bar gauge NOVEC 1230 clean agent. So it is like FM200. So it is also a clean agent. Is considered as per the decision by the company. NOVEC 1230 system design is as per Nfpa 2001. Design concentration of NOVEC 1230 at room temperature of 21 degrees is taken as 4.725% as per the recommendation by the vendor according to Nfpa 2001. Flooding factor is referred as 0.6873 kg per cubic meter as per recommendation by the vendor as well according to Nfpa 2001. Dimensions of the MCI building are referred from the existing layout drawing, and the dimensions are also verified during the site survey. Central banking system and selected directional valve concept is considered. 100% connected standby clean agent filled cylinder system is also considered. For the NOVEC 1230 clean agent demand calculations at the main control room and powerhouse control room, the total area of the room was 198.81 meter square. This was the height, room height, and then this is the ceiling void height, and then this is the floor void height. So these heights were taken during the site survey. The room volume was 536.8 cubic meter. Ceiling void, this one, floor void, this one, total volume was 668 cubic meter. So the NOVEC 1230 minimum agent required is, the formula is total volume into the flooding factor. The flooding factor is 0.6873 as per the Nfpa. So multiplied by the volume. So the minimum requirement of the clean agent was 460 kg. Similarly, at the UPS room, total area was 60 square meter. This was the height. This was the ceiling void height, floor void height. Similarly, total volume was this, and multiplying by the flooding factor as per the Nfpa, the minimum requirement of the NOVEC 1230 was 140 kg at the UPS room. This is a generic sample layout. Now, the NOVEC 1230 required volume and the number of cylinders. So how many cylinders are required for that? As central banking and selected directional well concept is considered. So the design NOVIC 1230 capacity of the system is on the basis of highest in demand room. The clean agent demand for the main control room of MCR is the highest. So its clean agent demand would be governing scenario, which was 460 kg, because at UPS room the requirement was 140 and on the MCR it was 460. So this is the driving case. So one cylinder quantity was 92 kg as per the supplying vendor. The main cylinder bank requirement was 5 cylinders when we divide this, and the reserve cylinders bank requirement was is also 500% backup. So now let us move to the foam system design. Considering the recommendations of the FRA report and the assigned job scope by the client, following modifications are considered in existing foam system at the tank farm area. Total to install 100% connected reserve system to have extended fire protection and at the same time to replenish the foam concentrated in the main system, to check the adequacy of existing foam system piping diameters as well, and to upgrade the existing pressure proportioning system to bladder tank foam proportioning system, as bladder tank system stores the foam in the bladder and does not allow water to mix with foam. In bladder tank, foam is stored within the bladder and there is no contact with water inside the tank. When seawater mixes with foam, concentrate and impurities in seawater such as shells, marine growths, algae might fix with foam concentrate as well. The system can get blocked and will not be available while needed. The existing foam chambers do not match with NFPA 11 requirement. These are to be designed as per the NFPA 11. So now what are the design criteria as per the standards? The total foam generator stations were 4. Existing foam storage tanks are the pressure proportioning tanks. Existing 4 PPT foam storage tanks to be replaced with the bladder type foam storage tanks with 100% reserves. Total oil tanks to be protected are 14. Out of 14, 8 were of floated roof type and 6 were of fixed roof type. NFPA 11 is for the low, medium and high expansion foam, is mainly referred for carrying out the calculations. 3% fluoroprotein foam solution is considered as per existing system and as per the findings of the FRA report. The full service fire protection is considered for fixed roof tank as per NFPA 11. Rim seal fire protection is considered for floating roof tanks as per NFPA 11. Application rate for the fixed roof storage tank is considered as 4.1 LPM per meter square as per NFPA 11 table 5.2.5.2.2. Application time for the fixed roof crude oil storage tank is considered as 55 minutes and for the fixed roof diesel oil tank as 30 minutes. This is as per the table 5.2.5.2.2 of NFPA 11. Application rate for the floating roof tank is considered as 12.2 and this is also as per the table 5.3.5.1 of NFPA 11. The application time for the floating roof tank is considered as 20 minutes for floating roof tank as per NFPA 11. This table, rim seal fire protection is considered for floating roof tank as per this NFPA 11. The number of hose streams for each tank, minimum operating time of 10, 20 or 30 minutes as applicable, and discharge rate of 189 liter per minute based on the simultaneous operation of the required minimum number of hose stream is referred from NFPA 11 from table number 5.9.2.2 to 5.9.2.4. The foam demand for the initial piping filling of a particular tank is calculated from length and diameter of a piping for that particular tank. Total foam demand for a particular oil tank is calculated by adding foam demand for the tank firefighting foam demand for hose stream, and foam demand for the initial piping filling. Firewater operating pressure at inlet of new blooded tie foam tank is taken as 10.5 bar gauge from the same for the existing PPT tanks, where one foam generator station is installed for the protection of multiple oil storage tanks. The capacity of the foam concentrate bladder tank is selected on the basis of highest total foam demand by the tank. Number of foam chambers calculated on the basis of Nfpa 11 as per table 5.3, 5.3.1 for floating roof tanks, and as per table number 5.2, 5.2.1 Nfpa 11 for the fixed roof tank. The foam chambers to be equally spaced along the circumference of oil tanks. So for the calculation point of view, foam demand and capacity calculation point of view, there are two foam generator stations installed in the tank farm area for the fire protection of 4 oil storage tanks. Foam generator station 1. By foam generator station 1, total number of oil storage tanks to be protected are 2. One is floating roof and one is fixed roof tank. So below are the detailed description of the oil tanks to be protected by foam generator station number 1. The floating roof tank is of the bad crude oil. The service is bad crude oil. Fuel type is flammable liquid. Type of the tank is of the roof is floating roof. Rim seal fire protection is required for this one. Fire will be extinguished using foam solution by creating foam dam of width 0.6 meter at the floating roof. So the foam demand calculation for this tank, for the floating roof tank, is the diameter of the tank is 30 meters, radius is 15. The radius of the tank without the radius of a dam is 14.65. Height of the tank is 14.6 meters. Foam dam area is calculated with the help of this formula, and the foam solution flow rate for the tank A can be calculated by this formula. The foam demand calculations for storage tank A, foam solution demand for tank A into 20 minutes, foam concentrate demand for tank A 3%, and the foam concentrate for the hose streams can be calculated by this formula. Foam concentrate for piping filling can be calculated by this. So the total foam demand, we can see that foam solution for the flow rate for the tank A, this one, foam concentrate demand for the tank A, and then foam concentrate for the hose streams, and the foam concentrate for the piping filling. Total foam demand is 813.5 liters. Similarly, we can perform the same calculation for the tank B, which is a fixed roof. The service of the storage tank is pump run crude oil. Fuel type is flammable liquid as per Nfpa 11 section 3.3.9. The type of roof is fixed roof. Full surface fire protection is required for this tank. So the diameter of the tank, the height of the tank, the surface area. Foam solution flow rate for tank B is 201.88 LPM. And now the foam demand calculation for the foam solution demand. Similarly, for the foam concentrate demand for tank B and for the hose stream, for the piping filling can be calculated, and the total will be 400.5 liters. The total demand of the foam is 400.5 liters. So by foam generator station number 2, total number of oil storage tanks to be protected is 1, which is floating. We have discussed the foam generator station number 1. Now this is foam generator station number 2. So with the help of this foam generator station, total number of oil storage tanks to be protected is 1, which is a floating roof tank. So this is the detail of this tank. This is the crude oil storage tank. Fuel type is flammable liquid as per Nfpa 11 section 3.3.9. Type of roof is floating roof. Rim seal fire protection is required for this one. Fire will be extinguished using foam solution by creating foam dam of width 0.6 meter at the floating roof. So similar calculations for this one as well. Diameter, radius of the tank, radius of a tank without radius of a dam, height of the tank. We can calculate the foam dam area, and then we can calculate the foam solution flow rate for this tank, which is a floating roof tank, by multiplying it with a factor of 12.21 LPM per meter square. Similarly, we can calculate the foam demand calculations for this tank as foam solution demand for tank C into 20 minutes, and then multiplying this factor with 3%, we can get the foam concentrate demand, and then the foam concentrate demand for the whole stream and for the piping filling as well. So total foam demand for this storage tank C, which was the floating roof, is 1776.85 liters. So for foam generator station 1 and foam generator station 2, in one, the main foam generator station 1 bladder tank should have the capacity of 900 liters. 100% reserve foam generator station should also be there. And for the main foam generator station 2 bladder tank should have the capacity of 1800 liters with 100% reserve as well. So for 2, the total foam demand was 1776.85. So round it up to 1800 liters. So now the foam chambers calculation, how we can calculate the number of foam chambers. Number of foam chambers for the tanks can be calculated on the basis of Nfpa 11, table 5.3.5.3.1 for floating roof tanks, and Nfpa 11 for fixed roof tanks, this table. The foam chambers to be equally spaced along with the circumference of the oil tanks. Below are the calculations. Foam chambers are for all the tanks. For example, for tank A, which was floating roof, diameter, circumference of the tank, spacing between each chamber, and then as per the Nfpa, and then the minimum foam chambers required are the circumference divided by the spacing. We can get the minimum foam chambers required rounded up to 4. Similarly, for the fixed roof and for the floating roof of the tank C. So this was the summary. Foam generator station's capacity. For the station 1, 900 liters, we have calculated. For the station 2, 1800 liters, we have calculated. For the existing foam chambers for oil storage tanks as per Nfpa 11, storage tank A, okay, the existing number of foam chambers are more than minimum requirement as per Nfpa A. So these were the results. So number of foam chambers are more than the minimum requirement. Now let us move to the firewater demand. How we can calculate the firewater demand. The purpose of this part of the case study is to present the sample results of firewater calculations carried out to determine the capacity of the firewater pump requirements, firewater storage tank capacity, foam, proportional and storage tank capacities as well. So these are the firewater requirements. The maximum firewater demand estimation is based on the assumption that only one major incident occurs at any one time fire scenario likely to occur within the installation as per Nfpa 14. This is the requirement of Nfpa 14, the assumption. 30% loss from the firewater design rate can be expected to occur due to wind and evaporation. Firewater storage of 8 hours duration has been considered. The fire scenarios considered for the project are storage area, tap area, marine or port area, and utilities and offshore area as well. So there are different scenarios. In scenario 1, it is a fire on a mixed naphtha storage tank A. Scenario 2, fire on the light naphtha export storage tank B. Scenario 3 is fire on Para-xylene export storage tank G, and scenario 4 is the fire on benzene export storage tank J. So scenario 1, which was the fire on a mixed naphtha storage tank A, this is an external floating roof tank. Rim seal fire is considered as a credible scenario. Fire will be extinguished using foam solution by creating foam dam of width 0.6 meter at the floating roof tank A. Cooling adjacent storage tanks B and C. The exposed surface is the half the parameter of the shell in front of the flame radiation. So now we are calculating the foam calculations for the tank. The diameter of the tank was 83.51 meters. This was the height, and we can calculate the area by this formula. Foam solution application rate of the external floating roof tank as per the NFP 11 table B.1 is 12.2. Foam solution application rate for the tank, we can multiply area with this factor, which is the foam solution application rate 12.2. We can get this value, we can convert this into cubic meter per hour. So it is 114.35 cubic meter per hour, the foam solution application rate of the tank. So considering 3% foam application, foam concentration required for the tank is 3%. 3% means 0.03. We can multiply this this value with this 3%. We can get the answer foam concentration required for the tank. Now the foam application duration for the tank is 20 minutes. So we can calculate the foam concentration quantity for the tank, which is 1.14 cubic meter. The water required for making foam solution for the tank is this one, which is 36.97 cubic meter. So for the dike as well, only oil spillage is considered in the dike area since it is not practical to cover a whole dike with foam. 4 into 450 liter per minute hose reel to be used to spill on the spill for 30 minutes, which is largely above the minimum requirement as per the codes and standards used. The foam required this much and water this much. This shall be facilitated by the portable monitors as well. So this is the cooling water calculation. The exposed surface area for the nearby tanks considering 3.7 meter rundown, because tank A got the fire and tank B and C were the adjacent tanks. So the exposed area is this much. Water application rate as per the API 2030 section 7.2.1 is 4.1 LPM per meter square. Water rate required for cooling the tanks is this. So we can get the water rate required for the cooling of the cooling the tanks. The exposed area multiplied by the water application rate. So the Firewater requirement for this cooling purpose is for the 8 hours, multiplying with 8 hours, it will be 6142.27 cubic meter. So an additional Firewater demand is envisaged considering simultaneous operation of 6 portable Firewater foam monitors. Foam requirement for the portable monitors shall be 10.8 cubic meter for 30-minute operation. So this is the summary for the storage tank A. Water rate considering contingency, Firewater demand, foam solution rate considering contingency, foam demand, and these are the extinguishing storage on fire, on dike, cooling adjacent storage tank, and total considering 30% contingency is the Firewater demand is 8107.22. So similarly for the second scenario, which was the fire on the light naphtha storage exposed storage tank B, it was the internal floating roof tank. Rim seal fire is considered as per NFPA section 5.4.2. 5.4.2. Fire will be extinguished using foam solution by creating foam dam at 0.6 meter at the floating roof. Also, foam will be supplied to the dike area of the concerned tank, which was D. Cooling adjacent tanks E and F, the exposed surface is a half perimeter of the shell in front of the flame radiation. So similarly, with the help of this diameter, height, we can calculate the area, and as per the application rate, as per NFP 11 table B.1, this is the rate. We can multiply this with area of the foam dam area. We can get the foam solution application rate for the tank, which is this value. So considering 3% foam application, we are multiplying it with 0.03, and with the duration 20 minutes, the foam concentration quantity of our tank will be 1.1 cubic meter. Water required for making foam solution for the tank will be 35.45 cubic meter. Then similarly for the dike as well, only oil spillage is considered in the dike area, since it is not practical to cover the whole dike with foam. 450 liter per minute hose reels to be used on the spill for 30 minutes, which is largely above the minimum requirement as per code and standards. Foam required of this much and water this much shall be facilitated by the portable monitors. Similarly, for the cooling water calculations for the adjacent tanks, for tank E and F, application rate as per the API 2030 section 7.2.1, which is 4.1 LPM per meter square. Water rate required for cooling water in a tank will be this much area. Multiplying with this application rate, we will get the water rate required for the cooling of the tanks, cubic meter per hour. Water rate. Cooling water, and now Firewater requirements, multiplying by 8 hours, it will be this much. So this is the summary of tank D. Similarly, we have applied the same formulas on scenario number 3 and for scenario number 4 as well, which was the fire on benzene export storage tank J. We have calculated the area with the help of diameter and height, and then we have multiplied that foam dam area with the foam solution application rate of the external floating roof tank. We can get the foam solution application rate, which was 54.47 cubic meter per hour. And by considering 3% foam application, it will be foam concentration required for the tank is this, and the duration for the tank is 20 minutes. Multiplying this with 20 minutes and converting the units, changing the minutes into hours, and then we can get this 0.54 cubic meter. Water required for making foam solution is this, for the tank is 17.61 cubic meter. So similarly for the other, we have explained this is following the same way. And the cooling water for the adjacent tanks, tank J and tank K, the exposed surface area is this much, and the water application rate as per APA 2030 section 7.2.1 is 4.1 LPM per meter square. Water rate can be calculated by multiplying these two factors, these two values, and this is the result. And the cooling water and the fire water requirement will be this much, and this is the summary of this results at scenario 4. So the aromatics plant area, the fire water demand was 4,000 cubic meter per hour. The fire water demand of 720 cubic meter per hour is envisaged considering simultaneous operation of 6 fire water monitors, and for the utilities and offsite area, the fire water demand of 360 cubic meter per hour is envisaged considering simultaneous operation of 6 fire water hydrants. So the largest fire water demand at the utilities and offsite is at the utilities and offsite aromatic area, tap area. The foam reserve of foam AFFF concentrate at 3% to be provided, considering 30% contingency at storage locations are as follows. Foam concentrate tank capacity for mixed naphtha storage tank, it should be 1.5 cubic meter for 2 tanks. Similarly, for this tank, from the benzene storage tank, it should be 1 cubic meter of 2 tanks. For the usage of portable foam monitor, the foam reserve of 16 cubic meter of AFFF concentrate at 3% is to be kept in the facility. So this was the result. And the Firewater design factor or Firewater pumps point of view, the 1022 cubic meter per hour capacity of a Firewater pump is sufficient to meet the above Firewater demand. The design of the pump shall conform to Nfpa 20 requirements. Therefore, the configuration of the Firewater station will be as follows. 4 Firewater pumps will be operated, 3 electrical driven and 1 diesel driven Firewater pump. Capacity shall be this much. 1 Firewater diesel pump will be standby. Firewater standby pump capacity shall be 1022 cubic meter per hour. 2 jockey pumps with 60 cubic meter per hour of the capacity. So now storage tanks, Firewater storage tanks. The Firewater storage capacity should be 8 hours of the full flow demand of Firewater pump discharge at 100% operation, depending on the severity of the incident, in order to offer an overall 8 hours firefighting at full flow demand. 2 Firewater storage tanks of 16,000 cubic meter minimum capacity shall be provided. So this was all the active protections. Now the passive fire protection, proofing integrity management case study. So for this project, the objective was to conduct the passive fireproofing integrity management study for fire zone 14 as per pilot project of the onshore gas processing plant in client's facility against the requirements of the latest edition of API 2218. The study was required to support the close out of actions from an audit of the PFP passive fireproofing at the plant. The scope of work was to undertake a gap analysis of passive fire protection requirements for an area as a pilot project of the onshore gas processing plant in client's facility against the requirements of API 2218. The other relevant industry guidance to identify any areas where either PFP can be removed or additional passive fire protection is required. Then the scope was to review the fireproofing of pipe sports for a sample of an area of plant based on the learning from the 𝐒𝐲𝐬𝐬𝐬 incident. Provide the technical information and estimate cost for undertaking a gap analysis review of passive fire protection for the balance areas, including a gap analysis for the fireproofing of pipe sports against new version of API 2218 for the other areas of the site, and identify any areas where either PFP can be removed or additional PFP is required. Condition assessment, assess the existing condition of PFP for the other units as well. Project milestone was to development of the passive fire protection integrity management framework, development of PFP operational performance standard, assessment of PFP requirements for one area, which was Fire Zone 14 as a pilot project against the requirements of the client design specifications, latest edition of API 2218 and other relevant industry guidance to identify the gaps and any area where either PFP can be removed or additional PFP is required. Site visit and fireproofing inspection to assess the condition of PFP and identify any areas where either PFP can be removed or additional PFP is required. And this was the methodology followed. The gap analysis study has been carried out based on the visual inspection and the collection of relevant information from the client. Guidelines provided in client specifications and API 2218 are considered as the basis for the study. Each item in the plant, such as pipe racks, multi-level equipment structures, air cooler sports, pipe sports, fire potential equipment, ESDVs, cable trays, long bolt valves were assessed as a part of this study. Based on the study, a PFP management framework strategy is prepared, which will be used for the implementation of gaps in the other areas of the plant as well. So, these were the deliverables for this study. PFP integrity management framework strategy, PFP performance standard, anomalies, severity levels, gap analysis report, PFP asset register, PMIR for PFP, cost estimate for the ballast areas as well. So this is the passive fireproofing or prevention for the pipe sport. This is the transfer line sports, and this transfer lines with hangers. Equipment structure in the fire scenario envelope. So in the fire scenario envelope, structure supporting fire potential equipment in the fire scenario area. For the pipe, consider the fireproofing all levels below fire potential equipment. No fireproofing on non-loaded bearing bracing. And then consider the fireproofing regardless of elevation above the grade. So this was the structure supporting fire potential equipment in the fire scenario area. And this is the fire supporting fire potential and non-fire potential equipment in the fire scenario area. Structure supporting non-fire potential equipment in the fire scenario area. And this is the pipe rack without pumps in a fire scenario area. So this is the fireproofing. This dashed line is the fireproofing. And this is the pipe rack with large fire potential pumps installed below. So consider fireproofing knee bracing supporting vertical load as well. So air fin fan cooler in the envelope. So this is the fireproofing and the equipment supporting structure. Steel structures are supporting fire potential equipment located within the fire scenario envelope shall be fireproofed up to the highest level at which the equipment is supported. Fireproofing applied to skirt of all the fire potential equipment are found satisfactory and in compliance with the client's product specification and as per the API 221A. For the pipe racks were made up of pre-cast concentrate elements, which itself is the fireproofing material, and extent of coverage is found satisfactory with no integrity anomaly identified. Transfer line sports. So for the some of the pipe sports which are sporting loads from the lines originating from fire hazardous equipment within a fire scenario envelope from the equipment shall be fireproofed. For the pipe sports, the red circled is the need to be fireproofed sports in the FSC. So these are the air coolers. So the air cooler sport legs on the top of the pipe rack, which are in a fire scenario envelope, are not to be fireproofed in the fire zone area 14 as per the client product specification and shall be fireproofed as per the client specification API 2218 section 5.1.2.2. All the members below the air cooler till grade shall be fireproofed. So this was the calculation of this passive fireproofing. All the existing PFP are meeting the requirements of the project specification as per the API 2218 code. Most of the items in fire zone 14 are sufficiently protected with passive fireproofing material except air cooler sports. Totally 11 air cooler sports and some pipe sports in close proximity to fire potential equipment are not having enough fireproofing. Client specification shall be upgraded as per the latest requirement of the API 2218 code. Inspection management plans shall be implemented for civil and structural assets for monitoring the PFP. Other conclusion was cable trays are of fire retardant type, so no cable trays are fireproofed as per API 2218. Protection may be considered if trays with cables servicing neighboring units run through the fire scenario envelope. A loss control review may indicate need for fire protection as replacement of critical electrical feeder lines and rewiring cable trays after a fire can be very time consuming. Power and instrument cable can quickly be destroyed in a fire, impeding the ability to have a controlled shutdown. So questions and answers. Just a moment. Yeah, yes, Mr. K, you can ask a question.
Okay. Let's ask first the previous questions that we haven't answered earlier in the part of the webinar. Okay.
Louder.
Okay. The difference between the pressurization system and pressure relief system is not clear. Please explain.
See, relief system and pressurized system for the normal process engineers or normal engineering people, like in any plant, when fluid is or gas or oil or water is being transferred from one end of the plant to other plant and other part of the plant, you are using pumps and compressors. And it means the fluids are pressurized from, as me code requirement point of view, from 1 bar to maybe 300 bar, right? So it's a huge difference is there. Like in normal hydrocarbons are operating between 20 to 30 bar or 40 bars, whereas ammonia plant is being operated as 300 bars. So this pressure, this system is called pressurized system, and the same system when you need to like a relief or you want to release the fluid to a low pressure zone in case of there's a problem with the system. For that reason, you need a relief system to flare or to atmosphere. I hope it's clear now.
Okay. Next question. For electrical room that use the CO automatic fire system has a possibility for error. It comes from error detection by smoke or fire device. If it happened, the system will be active even on no fire. So could it harm the people there? How can you prevent that risk or any advice?
See, the normal design part in the control room and or the substation especially, it is assumed that they're unmanned when people are going for maintenance activity inside the substation. At that time, this system is put on bypass. This system will not be activated while operators are or maintenance crew is inside the substation. So it is a part of the parcel of the any work permit system. When you're entering into the substation, you have to first isolate this automated fire protection system, which is meant on either CO2 or FM200. It's a normal part of the design.
Okay, next question. Usually PFP on structures is considered as SCE. What is the maintenance/inspection we can do on that, and what is the frequency we need to do for the inspection? Is there any Nfpa guideline or recommendation?
See, I think you're referring to API 2218 based fireproofing, which is done for 1 hour fire rating on the structures, like up to first layer of the pipe racks, or if you equipment up to final rack, or the first rack of the or first level of the platforms where equipments are there. So the normal frequency of visual inspection of these structures is about 5 years. And if there is any signs of crack or damage, then the repair is required. In general sense, whether you're using a mastic material or you're using cemented material, calcium silicate based, the frequency, like average frequency is 5 years. It's not like hard and fast.
Okay, next question. Are lighting arrestor recommended for storage tanks, storage risk?
Yeah. So lightning protection is important for the storage tanks because there's a potential of lightning attack on the storage tanks. And personally, I have witnessed one fire initiated during, I think it was the month of February in Abu Dhabi, where lightning struck to one of the storage tank and the fire was initiated. So if lightning protection and earthing is not properly done, there is a big risk.
Okay, next question. Does a positive displacement foam pump require a minimum flow or pressure control at its outlet? Our installation has only a PSV at the discharge line, which poses a problem if minimum flow is utilized from the foam.
See, in normal, centrifugal pumps are used, and the Velosi system is being used to suck the basically substrate to make foam. That is a more effective system. And when you're pushing substrate via positive displacement pump, there's a powder solution, it might be having some problems. So I'm not so familiar with that kind of design. Like in normal foam system, we know we do not observe this kind of problem, and positive displacement pumps are not used in foam system. That's what my experience is, and of course there could be other options available which I might not be aware.
Next question. Is lake, river, or seawater suitable to be used as a firewater source?
See, as a backup system, any kind of water can be used, but there should be a cleaning and corrosion prevention mechanism to be in place so as the system could be retained back to a normal operation afterwards. Otherwise, if you would be using seawater, it will be very corrosive and it can cause the highest corrosion in the firewater network. I have seen at least at one facility where the wastewater from the plant was being used, or uh, the water which was removed, separated from oil or condensate, that was used for firefighting, and it caused very high corrosions. And within the next 5 years, the last operation life of 5 years, all firefighting system was damaged because the water was very corrosive. So the important thing is the corrosivity of the water has to be managed so as the asset life or firefighting system life is not compromised.
Next question. Due to design root issue between the MV cable and the deluge pipe, the MV cable has almost touched the pipe. How much the required distance between the two systems and what to consider during design stage?
See, the basic guideline regarding plant design stage. Yes, on the pipe racks at one corner you will see the pipe, sorry, the cable trays, and at the side there are pipes. But in general terms, we don't expect any kind of leakage of the electric current from the pipe to metallic structure. So as such, they go side by side, but should not be touching. This is the normal expectation if the cables are above ground and on the cable trays. This is normal concept. And then there's you need to differentiate between electrical cable and instrumentation cables, because sometimes there could be a magnetic flux created by electrical cables and which may impact the signal of instrument cables. So there are basic IEC guidelines which should be followed while making plant layout with respect to the cable layout.
Okay, next question. Switch gear control of FM 200 or 600. Should it be manual or auto if manned?
Both are, if manned.
Hmm.
No, see, if manned is different criteria. If manned, it should be manual. If unmanned, it could be auto.
Next question. What are your thoughts on fire water tank design that combines raw water and fire water in a single tank? Is it a good design? What are the key things to look at this tank design?
See, if you're using raw water, mean portable water or your water you can drink. So drinking water is clean water, which can be used as a fire water. But the important thing is, if the potable water is being used for normal life, and if its level and the storage capacity is compromised, and on any given day, if that water is used for normal service, normal plant wash and drinking or some other purposes, and on the day of the fire, the level of the tank is not enough to sustain or support the fire scenario, then it could be dangerous. So to ensure that water would be there at the time of demand, that is a challenge if you are having two services from the same tank.
Okay, next question. As per Nfpa foam is suitable media for extinguishing of chemical fire, UN class 3, but we see water sprinkler system in chemical storage warehouses. Which standard is considered to have water sprinkler system in chemical warehouse?
See, it's a very like a serious issue. The compatibility of water sprinkler system or water spray on the chemical to be studied. Just like if you have two chemicals, acid and base, you try not to mix them, because if you try to mix them, there could be explosion. Similarly, if let's assume there's a sodium metal is kept in that storage where you are saying chemical, if water and sodium is mixed, there's a big explosion. So compatibility of firefighting media with the storage chemicals should be carefully studied, and then you are designing the firefighting system. So in general sense, it's not done with closed eyes.
Next question. Does NFPA specify inspection requirement for sprinkler system? If yes, what is the frequency and method?
See, this frequency is given in the NFPA, like yearly, bi-yearly, depending upon the nature of the system what you are applying. And mostly companies are using it. There is a requirement of functional testing requirement from a firefighting system.
How to check the integrity of the sprinklers after years of no fire-related accidents happen?
So the functional testing is required. That is the one of the purposes, and one of the objective of functional testing is.
For tank protection water system, how many rings should be used and at which height? Also, how spray nozzles are selected?
See, as per NFPA 2030 guideline is there. In NFPA 30, this guideline is also there. The purpose is the cooling, and if the cooling point of view, how much water density is required to be thrown in the given area, that will determine the kind of nozzles or sprinklers and number of nozzles and sprinkler to be installed, and it will also depend what the diameter of the tank is.
Next question. Does a positive displacement foam pump require a minimum flow or pressure control as its outlet? Our installation has only PSV at the discharge line, which poses. Oh, this is the repeated question. Apologies. Another question. How are air coolers support fireproofed? Which material is used for fireproofing?
See, for air cooler, air cooler means, yes, for the fluid. Normally, if pipe racks are supporting air coolers, so they should be fireproofed up to top layer, top tier, and the fireproofing can be done by the mastic material, or it could be done with calcium silicate cement. Both options are acceptable.
Okay, we can have one more question.
Sure.
Okay. So for gas turbine, the fire extension system with CO2 bottles include 2 discharge line, 1 quick and the second low. Why?
See, this could be a supporting point of view, what I understand from the question, right? And in gas turbine, sometimes it's manned, so the same concept of substation has to be followed. So, but the redundancy of the system is provided. Like if one system is utilized during testing, the other system is available. So it's the 2 systems are provided just to provide redundancy or standby capability of the system. So it concludes our discussion, and we've taken 30 minutes extra. We hope that this webinar would be useful for the engineers, and we will also be placing this video of the webinar on our web page via YouTube. So you can get the information from there as well. Certificates would also be issued to all the participants. And thank you very much, everyone, for attending this webinar. And we look forward to having you on board for our next upcoming webinar. Thank you. Bye-bye.